Okay, in the last video we proved part 1 of the extended linearity principle. So in this video we are proving part 2. So once again, we've got a differential equation that corresponds to a forced harmonic oscillator. I'm calling that star. And then I've got the associated homogeneous equation. Part 2 of the extended linearity principle says this: if yp and yq are both solutions to star, then the difference between them is a solution to the associated homogeneous equation. Okay, so as always for a proof, I need to suppose the if. Suppose yp and yq are solutions to star. Then, what does that tell me? I just want to spell out what does it mean to be a solution. I know that yp double prime plus p yp prime plus q yp is equal to g of t. In other words, if I plug yp into star, it works. I get a true equation. Let's call that smiley face. Okay. Also, I know that the same is true for yq. So yq double prime plus p times yq prime plus, plus q times yq, is equal to g of t. It's a little weird using p's and q's for these constant coefficients and also these subscripts, but I am going to go with the notation from the book. Okay. We will call that monster. Okay. So these are our suppositions. Now my claim is that yp minus yq is a solution to the associated homogeneous equation. And let's spell out what that means. That is that yp minus yq double prime plus p times yp minus yq prime plus q times yp minus yq would have to equal 0, because I'm supposing that this is a solution to the associated homogeneous. So that's my claim, just written as an equation. Okay, so I want to prove that. I'm going to start with this left-hand side here. Notice the right-hand side is just 0, so I'm hoping when I simplify, I can make everything drop out. Now, I'm going to clear myself some board space here, so I'm going to erase this. I think we should be able to remember what smiley face and monster were, because they are both just that they're solutions to star, so that if I plug those in, I get a true equation. So, if I look at my left-hand side, that was yp minus yq double prime plus p times yp minus yq prime plus q times yp minus yq. So that was just the left-hand side of this equation with yp minus yq plugged in. So let's simplify. I'm going to use the sum rule for, the difference rule, I guess, for derivatives, because I'm subtracting. So if I subtract two functions and then take the second derivative, that's equivalent to taking the second derivatives and then subtracting. Same thing for first derivative, so this will be just yp prime minus yq prime plus q times yp minus yq. So here, I used the difference rule for derivatives, both first and second. Now, I'm just going to distribute my p's and my q's. So yp double prime minus yq double prime plus p yp prime minus p yq prime plus q times yp minus q times yq. Okay, so this is just distributing p P and Q. Okay. But now I've got 1, 2, 3, 4, 5, 6 terms connected by addition and subtraction. Now I do need to be careful. The terms I'm subtracting have to stay negative. Okay? But if I view that subtraction as just adding the opposite, I can move these terms around and regroup them, just realizing that the negative sign has to stay with each piece. So I'm going to do what we did last time. I'm going to group them as the P terms and the Q terms. So the P terms, that's going to be this one and this one and this one. That's going to give me yp double prime plus P times yp prime minus Q, plus Q times yp, okay? And then these terms, well, they're all being subtracted. I could, if I want to, factor out that negative. Let's actually do this in 2 steps. So I'm going to say this is plus negative yq double prime minus p yq prime minus q yq. So there I just rearranged the terms, again using the commutative and associative laws. Now I'm going to factor out the negative 1. So I'm going to get yp double prime plus p yp prime plus q yp minus yq double prime plus p yq plus p yq prime plus q yq. So this is just factoring out a negative. But now I can say by smiley face and monster, I knew what this was equal to. That was equal to g of t because yp was a solution to star. This was also equal to g of t because yq was a solution to star. So I'm going to get g of t minus g of t, which is 0, which was the right-hand side of my claim. Now, I'm going to just write QED to indicate that I am not stopping because I have completely run out of room on the board. I am stopping because I have actually accomplished what we set out to do, which was to prove part 2 of the linearity principle. Extended linearity principle.